9.2 is talking about angles and their measures. Let's see if I can get this thing cleaned up just a little bit for us here. That's a little better. Okay. You guys have thought about angles as being these like kind of static little measurements inside shapes and stuff like that. And your angles could never get any larger than 180 degrees, right? When you learned about them in geometry, you're pretty much stuck to that. Can't make an angle bigger than 180 degrees. You always find within shapes and things like that. So we're going to kind of expand your idea of angle today a little bit, and don't think of angles necessarily as these like little, like I said, little static things that have to be just so. Think of it more as a rotation. Okay, so where did it start, where did it stop, and how far did it keep going around? So, and we're going to talk about this on the coordinate plane. So if we have, and we only use the coordinate plane guide. Okay, so rotations on the coordinate plane always start at, well, they have to come off the origin though, because remember, an angle is two rays, right? It's got a starting ray and an ending ray. So our starting ray, if we're thinking about it as a rotation, is always going to be along the positive x-axis. Okay, we call our initial point. Okay, or an initial point or initial ray, side. I guess I'll just say side. Okay, and then it's just a matter of, think about it almost like hands on a clock, except they're moving backwards. Okay, we actually rotate counterclockwise. So if we start from there and we start to rotate, okay. So if we had something like it came up and ended up over here somewhere, so it'd be like this rotation from the side to that terminal side. All right, and then we could measure how many degrees that is. That angle that I made right there looks like what kind of angle? Obtuse. Yeah, so I've made, maybe it's like 120 degrees or something like that. I don't know. But yeah, so it would just be like a rotation from the side to that terminal side. Before, where you couldn't go above 180 degrees, now you can. So if we've got our initial side over here again, coming off that positive x-axis, and maybe it stops down over here. So that rotation actually goes all the way like that. Okay? And we can still measure that. Okay? So 180 degrees, right? You see that? 180 degrees would be a straight angle, right? Both sides go opposite each other. This one's actually been rotated even further than that. So measure that too. Okay? Put a degree measurement to that and see what we have.
So an angle measure goes counterclockwise?
What?
So an angle measure goes counterclockwise?
It always, yeah, we always measure them counterclockwise. Mm-hmm. So, and I brought that up. We go both ways. If it's clockwise, it's a positive rotation. If it's clockwise, it's a negative rotation. So I'm just going to write that down because that's important. Okay, so rotation. And clockwise, it's a negative rotation. All right, so what I'm going to do is I'm going to show you some angles, and I'm going to give you some little measurements in degrees on the picture somewhere, and I want you to tell me what the overall rotation is. How many degrees is the overall rotation for each one of these? Okay? All right, so let's start with this one. You guys all see what angle that is in there that I put in there? It's a 30, yeah. So if that little angle in there is 30 degrees, how much is the actual whole rotation then? 210, right. It's a 210 degree rotation on that one. Okay, does everybody see that? Right, because 180 gets you to the straight angle, and then it's 30 more than that, so it's 210. All right. What about that rotation? And let's say this is 40 degrees in there. 320. How'd you get 320? Good, because a full rotation is how many degrees? 360, right? So 360 minus the 40, we've got a 320 there. All right. Let's do at least maybe two more here. I'm not even going to put anything on there. What's that one? Good job. Yeah. Everybody see that? When we're looking at a coordinate plane, the two axes, the x and the y axes, are always 90 degrees to each other, right? They're perpendicular. So that rotation, it's going 90 degrees, but notice how it's going clockwise there instead of counterclockwise now. Okay, so it's negative 90 degrees to get to that. All right, I got one more. This may or may not blow your mind. We'll see. Okay. We're going to put it out over here. This is going to be a 45-degree angle. And I want... Just write it down. I've made a rotation that's more than one time. So what do you think? How would you do that? Teresa? What do you think?
Wouldn't you just do 360 to 90 and then 45?
Yeah. Yeah, because you got 360, gets you all the way around once, and then there's 90, and then 45, right? So 360 plus 45, or 360 plus 90 plus 45, 2, was it? For what? 495? Okay. Going close, or right? So this is a positive 495 degree rotation then. Okay. So at angles as rotations like this, even if you go more than one full time around, that sort of thing, that's important for us later on when we're going to be doing some trigonometric calculations that are outside of just right triangles. We're going to do sines, cosines, tangents, not just for the angles you see in a triangle, for all of these kind of angles too. Positive, negative, more than 360, stuff like that too. So being able to look at a picture and identify what you've got there is like an important first step to being able to do that. So that's why we talk about it. Since we're talking about stuff, it'd probably be a good time to talk about what it means to be coterminal. What's the prefix co mean? No. No. Together. Yes. Co means together. So what do you suppose coterminal means? Oh, okay. Let's go back. Initial side, terminal side. What's the terminal side? The end. You guys, when you go to the airport, you ever go to the terminal? You know why it's called the terminal? because it's the end of the walkway where you get on the plane. It's the end of where you're walking to get to it. That's why it's. It is. So, terminal means end. Okay? So if you're going to terminate something, like the Terminator, you're going to kill somebody. Anyway, so to terminate means to end, right? So means that there are two angles that end in the same place. Okay? So if I have an angle, say, I don't know, 90 degrees. Okay? So if I draw degrees, that looks like this. Another angle that terminates, that ends in the same place as 90 degrees. Okay? Couple different ways I could go get that. I could do another positive rotation, but just go all the way around and come back to it. Or I could do a negative rotation and try and get to it that way. Okay? But it has to end in the same place. Okay? So if I went this direction, like that, do you see how that's coterminal? Stops in that same place still? Okay, but what's the angle if I go that way, though? Careful. Negative 270. Yeah. So negative 270 degrees. That's one of them. Anybody think of another one? Somebody just said it. Where was that? 450. Okay. 450.
Can't they just keep going?
Yeah. She just did 360 plus 9, right? So that would start like here and go all the way around and then come back to there like that. And then Cole made a good point that you could just keep doing this, right? You could just keep going around and around and around, and you keep adding 360, and you keep getting more coterminal angles, right? So technically, coterminal with one, there's an infinite number of answers you could give me. Now, there are some that are right and some that are wrong, but technically you could just keep going with it and keep giving me more and more and more. But that's the idea, though, with coterminal, okay? Has to end in the same place. Yeah? Correct. Mm-hmm. Yep. Took the words out of my mouth. So adding, subtracting 360 degrees is what we're doing. Yep. Start with your angle, whatever it is, and add or subtract 360, however many times you want. So negative 270, guess how we got that? 90 minus 360, negative 270. 90 plus 360, 450. And on and on and on, right? Okay. So that's... you guys have only ever used degrees to measure angles, correct?
Correct.
There are technically two ways. There are technically two ways to measure angles. And the other way is using something called a radian. And actually, to be fair, a radian was here before a degree was here. People were measuring in radians before they were measuring in degrees. And in some ways, radians make a little bit more sense to use rather than degrees. The only reason that people use degrees or have using degrees is because they're easy to work with. 360, why the heck make 360 all the way around a circle? Why not like 100 or something? Why is it 360? Any ideas? There's a reason why they said that, though. That's true, but it's not exactly the same. But the only reason that 360 is used is because it is highly divisible. You can break, a lot of numbers go into 360. You can break it up into lots of nice, even pieces. 360 you can divide by 4, you can divide by 2, you can divide by 3, you can divide by 6, you can divide by 5. So if you have a full rotation and you only want to go like a fifth of the way, well, then you have a nice, neat number. There's no decimals to get in your way. It's just 360 divided by 5, which I can't do in my head for some reason. 72 degrees. Nice. 360. I want to break it into 4 equal pieces, 90 degrees. Nice. I want to break it into 8 equal pieces, 45 degrees each. Nice. It works out great every time. Okay? That's the only reason why they did 360. It's because you can break it into nice equal chunks that way. The other way that we measure with radians, this was developed based on the radius of a circle. Okay, so do a little demonstration here. See how well it goes. But essentially, one is the angle that is formed if you were to take the radius of a circle, pick it up, lay it down on the circle, and then figure out how much of the circle that is. That angle that it makes on the outside of the circle, that's 1 radian. Okay, so I'm going to try to do this with my compass here. It takes practice. All right, so there's my circle. Sun here. Try and make this thing as accurate as I can. Okay. So there's my radius. And you obviously don't need to write this down right now if you don't want to. My radius, and that radius, and like pick it up and put it on the curve of the circle. Okay, so I do that. So I'm going to use string to kind of work this out. Then, so my little piece of string, I want to take a piece of string that is the length of the radius of this circle, so I can pick it up and use it. So there's about the center. So we're about right here. Where I marked the Sharpie on the string, that distance from the edge of the string is 1 radius of the circle. Okay? So if I do this and put it here, and then I'm going to try this down on the circle, so we get to about there-ish. Okay, so that much, if this is my initial side, and this is my terminal side, the angle that I've just created right there is 1 radian. I've taken 1 radius, put it on the circle, and the angle that got made from that is 1 radian. Okay, so this little angle right here, one radian. Okay? Okay? We can fit into a circle. Okay. So yeah, you guys think, what about 6? Based on what we got so far? So, all right, there's about 2. So there's my second one. There's the third one. Okay, from there. Nope. There's 4. So there is 4, about, or 5 right there. There's 5. And then 6 be about to there-ish. So, here already you're seeing why students in general don't enjoy radians as much as degrees, because it doesn't have that nice even thing going on, right? How many radians in a circle? 6 point, I don't know, something. A little bit more than 6. So, if you take, let's say, half a circle, okay, it's going to help us, because then we just multiply it by 2. So this is, if you just look at the top of this for a second, okay? So just looking at the top, 1, 3, and a little extra. What number have you used before that's 3 and a little more? Pi, 3.14159, etc., etc., etc. Guess how many radians there are in half a circle? Pi. Say how many are in an entire? 2 pi. Okay? So, yeah, it's not even a number of radians in a circle. It's pi. It's 2 pi. Okay? So it's this irrational number that has a repeating decimal or decimal that goes on forever. It's not a real nice number to work with. So what you find is when you generally are looking at angles in circles, radians, almost always you're going to see the little letter pi next to it. It's so many pi radians or whatever, that sort of thing, because they don't fit nice and neat into the circle. Okay? So we're going to use that idea to help degrees and radians and angles in radians instead of degrees and that sort of thing. Okay? So let's see. So one rotation in degrees is what? 360. Okay. One rotation in radians is 2 pi. And actually there is no symbol for radians. If you want to write like rad after it or something, okay, I'll take that. Or a little r or something. But generally, if it's going to be in radians, there's just nothing there. So if you have a measurement and you're curious, is this degrees or is this radians? I don't know what it is. If you see a little degree symbol, you know it's degrees. If you don't, you know it's radians. Even if it doesn't have a pi. Could still be radians, even if it doesn't have a pi. Now, right? 360 degrees is equal to 2 pi radians, right? Okay. Break that down a little bit more. Think of it like a fraction. If 360 degrees is 2 pi, 180 is 1 pi, like we talked about. In your homework last night, we're doing all that little, like, changing the days, or what was it, changing frames into seconds. We're doing all that dimensional analysis stuff. We can do that with this too. Okay? Correct. You're welcome. So if radians, but because I have a ratio of how many radians to how many degrees, and I can multiply by that ratio to cancel and get what I want. Okay? So 45 is, if I use this pi thing here, I want it in radians. I want to cancel degrees. What should be the fraction I multiply by then? Pi over 180. Yeah. You guys will catch that? This represents this relationship, that 180 is equal to pi radians. So if I convert into radians, I need to cancel and have radians left over. Do you see how this is going to cancel the degrees? Because degrees is underneath. Okay. So, and I'm not approximations. I'm going to leave everything with a pi in it. Okay. So before you start typing it into your calculator here, it's 45 pi over 180. But 45 over 180, that part of it can simplify, right? How many times does 45 go into 180? 4 times. So what is this then as a simplified 1/4 times pi, or if you would rather, just pi over 4. Does that make sense? Because it would be 1 times pi over 4. So just pi over 4. Okay.
Please excuse the interruption. We have a few announcements. Anyone interested in traveling to Costa Rica in the summer of 2016, please come to an informational meeting today at 5 o'clock in room 2101. If you are not able to make it but would like information, please see Mrs. Postma. Also, the first hour econ continues to sell Team Winchester Baby Egg t-shirts for $12 each at both lunches and in Mr. Weir's classroom. They're also having a dodgeball tournament on February 21st from 5 to 8 p.m. in the high school gym. The cost for a team of minimum 6 players is $10. Come and watch. The entry fee is $3. There will be discussions and live music, so please go and have fun. Thank you.
Yeah. Okay. 3 radians, and I want to turn it into degrees. What now? Yeah. Okay. Well, tell me how to do it. How do I get there?
Well, I just do that, well, if you divide it 180 by 4, you're getting 45.
Mm-hmm.
So you do the same to pi. And so I figured that if it's pi divided by 3, it'd just be 180 divided by 3.
Yeah. If you can reason it out in your head, thinking about it kind of proportionally, absolutely. If you do it by, this works too, okay? And leave degrees, then you can multiply like that, okay? So I like the way you're thinking about this one, though. I like that a lot, because he's visualizing, are you like thinking about like half the circle? Is that how you're doing that? Thinking the top half of the circle, okay, pi over 3 would be 3 equal chunks of that top half. The top half is 180 degrees. Divide that by 3, that's going to be 60 degrees, right? So in this, we end up doing that, too, because if you look at the here, what's going to happen with 2 pi's? Those are going to cancel each other out, leaving 180 divided by 3, which is 60 degrees, right? So if you want to try to visualize it in your head and think about it that way, for these, that'll work just fine. Some of them are a little more challenging where you might not be able to do that, but if you can, go for it, because that's going to help you down the road, I think, too, being able to visualize what we're doing with some of this stuff. These things called sectors.
Are we close to talking about vectors?
No.
Oh, yeah. Mrs. Smith knows that. Yeah, she's a great teacher.
So, here is a sector. Hey, just pay attention to what we're doing. So, sectors is just the math way of saying a chunk of a circle. Okay, it's a piece of a circle that's kind of pizza. Okay, the middle of it goes to the center of the circle. Okay, and you're taking out that slice. Okay, and so whatever angle you have here, that angle out of 360, if you're talking degrees, or that angle out of 2 pi, it's that ratio of the circle. Okay? But the sector is just that little piece of pizza. So the next time you're having pizza, you can tell your parents, oh, these are great sectors. Thank you. And watch their face and see how confused they look. So, sectors, we're going to figure out the area of a sector. And we're also going to look at the arc length. So how much arc is there on the outside of a sector? So let's start with this. For the area of a circle, what is that? You guys used that in your homework last night too.
I didn't know the
Pi r squared. Okay. Area equals pi r squared. Okay. So, if you're taking, and in here is, if you take theta and you divide it by 2 pi, that's what ratio of the circle you have. Does that make sense? Because 2 pi is the whole way around. So whatever that angle is out of 2 pi, that's like the percentage of the circle that you have. Okay? So it's a percentage of the area. So if you take theta 2 pi multiply pi r squared, you have that percentage or that portion of the whole area pi r squared. And so then you have the area of that sector. So for the sector, now it can be simplified. As noticed, you've got a pi. So you can break this down into over 2 times r squared. So your angle divided by 2 times r squared, that's the area of a sector. Okay, so let's try. So let's say a circle has a diameter of 4 inches. What is the area of a sector that has an angle of pi over 5? Things we need to do the area of a sector, we need the angle and we need the radius, right? We have the angle, it's pi over 5. What's the radius? 2, okay. So the area of this sector then is going to be pi divided by 2 times 2 squared. All right, we're going to try and leave the pi in our answer here if we can. Okay, so pi 2. What's half of pi? Think about it logically with fractions. What's half of a fifth? 1/10. So what's half of pi over 5? Pi over 10, right? So this actually is pi over 10 times 2 squared is 4. So pi over 10 times 4 pi over 10, right? And then we can reduce that 2 pi over 5. And that would be measured in what? It's area, not inches. You're close, though. Inches squared, yeah. So, that's area. Thing. That's got a couple of things there. This is my arc length. I want to know how long is this. If I had my little piece of string that was between those 2 points, how long is the piece of string, kind of a thing. Well, what's all the way around the circle called? What's the arc length if we go all the way around? Circumference. What's the formula for circumference? Okay. And then over 2 pi is like the ratio of how much of that you have, right? So if we take the whole circumference and then multiply it by that little fraction, that'll give us the little piece. Okay? So S, the arc is your angle divided by 2 pi. So what fraction of the whole thing do you have? And multiply 2 pi r. And this formula ends up looking really simple when you're done. You cancel the whole 2 pi, yeah. So the arc length is just theta times r. That's it. That's it. So what is the arc length of an arc cut by, let's say the angle is 20 degrees with a circle that has a radius of 5 feet. So kind of a big circle. All right. Now, with this now. If I do a theta that's in degrees, you have to convert it to radians. Look at how we set it up. For 2 pi. 2 pi is measuring in what? Radians. So this formula is assuming that you're using radians, right? So I can't use a 20 and just plug it in. It's not times 5. Okay? Well, once you convert it, it is. So 20 degrees, we got to get it into radians. We know how to do that, though, right? Well, you'd have to do 20 times 80, right? So that would give you 20 pi over 180, but that reduced a whole bunch, right? That would be pi, right? Because 20 goes into 180 9 times. So our radian measurement is pi 9. Now we just take that, put it in. Okay, that's your theta. Pi. And your radius, we already said, was 5. So the arc length of this one then is pi 9 times. So what would that look like as just one fraction? Yeah. Over 9, what? Feet. Good, because we're talking about the length of something, right? So it'd still be in feet. Not just feet, because it's not area anymore. Okay. So with these two little formulas that I gave you to use for area of a sector, arc length, just be sure you're using radians. That's really the only big hiccup you're going to have with it, I think. Okay? If you're going to use an angle for those. Okay? Otherwise, I think we're good. So.